All right, let's go ahead and get started. Let me get the lights and whatnot. So I don't know if you all have noticed on MU Online, but I went ahead, I've graded homework 1. What I've decided to do to try and keep that simple is, since I don't really have anything to hand back to you, it's usually natural, like you turn in a homework, I give it back to you. Instead, what I've done is I kind of put together some comments for each of you so that you'll know why you got what you got. Okay, so Abdulila, all right, Isaac, okay, Shehu, all right, Tara, Mr. Ma, okay, Bassam, Vera, Akash, that's you. Mr. Spence, that's you. Ratna, that's you. That's you. Mr. Cleo, that's you. And Mr. Cooldeep's not here. Okay, all right. So I'll walk you through a couple things and some general comments that I found. So I've got the solution to the homework put up here. One thing I found kind of interesting is actually what I found is the class as a whole actually did better on problem 2 than they did on problem 1. And there was a couple little issues, but there was a big one associated with this matrix calc at the bottom, A transpose times B times A. 2 big issues. Number 1 is you can't change up the order of multiplication. It's not the same as with numbers. See, like with numbers, 5 times 3 is the same thing as 3 times 5. But with matrices, A times B is not necessarily B times A. They're not necessarily the same thing. So you have to maintain the order. So I think there was a couple of you that were like, well, I'll just do the A transpose times A and get that out of the way, and then multiply the B one on the outside, and you get a different answer. Well, because matrix multiplication is not commutative. It does not necessarily link up. All right. Okay, another thing, and this is something to keep in mind, and I think this happened more with the people that are more experienced with Excel. It's tempting to just literally write the multiplication symbol. Just use an asterisk for multiplication. You can't do that for matrix multiplication. You have to use mmult. So that happened quite a few times. And make sure that when you're using mmult that you highlight the entire region before you start typing and that you hit Control-Shift-Enter. Because your first cell will be right. Like if you just start typing here but you don't have the whole region highlighted, this answer will be right, but everything else will be wrong. Okay? All right, everybody good? And then for problem 2, the only point that I would make is I think just about everybody in here had the right idea behind what was going on. I'm not going to walk through the entire problem step by step because I think the summary sheets and whatnot that I've given you kind of give you the overall picture of what you did right or what you did wrong. But I mean, in the end, keep in mind, you all did very well on this. The one thing I'd kind of like to see is a kind of summary of your answers. It does not need to be, super neat. I think this is probably on the upper echelon of what you need to do. But just, some localized place where I can look at the Excel sheet and say, here's the answer. Okay, the problem was asking for the displacements of each of those bodies. So here's D2, D3, D4. And I say, here's the magnitude, and it's going to the left. I've got, the internal forces. I'm indicating which ones are compression, which ones are tension. This one actually came out to be 0. The support reactions and indicating their direction. It doesn't need to be, Rembrandt or Da Vinci, artwork in terms of its neatness. It just needs to be collected. I think about half of you, did a good enough job of collecting your answers in a place where I could, go through and review and say, hey, here it is. But for those of you who didn't, just make sure that you're summarizing your answers at the end. All in all, in terms of the class, I really don't have much else to say. You all did very well on it. Okay? Does anybody have any questions? All right, before we start digging into the notes, you all have an assignment due on Thursday. Hopefully, you all have at least started it. If you haven't, you're in for a busy couple days. So you tell me. Are you feeling confident? You got questions? You tell me. I mean, I don't mind to have this first little bit of the class just be sort of a, discussion and make sure everybody's fine with the homework. Again, I want to see you all succeed. I'm doing this for you all. I could go lecture to the janitor's closet if I wanted, but that wouldn't really do you all any good. So I want to make sure you're all doing well. You all have any questions on the homework? Okay, all right. All right, so here's what we're going to do today. So I'm going to start off by getting the sign-in sheet started and get that passed around. I sent you all an email that had 2 Excel files. We're going to look at those Excel files in some detail. And I chose to do that because I really don't feel that the stuff that's to come, at least for a little while, with our Excel usage, is introducing anything that's new in terms of Excel. The big thing that I wanted you all to understand with Excel, I want you to understand the assembly process. I want you to understand how to do matrix multiplication, matrix addition, scalar multiplication, transposes, inverses, all that, which you all, I think, have shown by now that you're capable of doing, and that you can follow through the process. Okay, the software usage, I think, was my first, goal in terms of doing a lot of this work, and I think by now we're good. Okay, so I really don't see the benefit of taking this example and then doing it together again like we did the first one and like we did the second one, just because there's nothing new here. Okay, but I did want to provide you at least some of the formulas and equations and whatnot so you could check your work and see what you did. Okay, so real quick, let's just make sure we're all on the same page. So we reviewed the stiffness matrix for a beam element. It looks something about like this. And then we went through the concept of non-nodal forces on elements, and basically we pull a little trick. We solve for our displacements by removing that fixed-in force effect, but when we express our final answer, we add it back to the final solution. So it's a little trick, but in the end it makes the analysis possible, and we're able to correctly account for those non-nodal force effects. Okay? Sound good? So we had this example. Again, the process should be old hat by now. We take the element, we define an analytical model, which for beams is pretty straightforward. It's just pretty linear. The assembly process for beams is about the simplest one that we're going to see. All right. We have our stiffness matrices, our K matrices for each element. Just again, making sure you're using consistent units. Another point to make, because we're dealing with systems that are all along the same coordinate system, we don't have to use beta matrices. So we don't have to deal with any of that. So we have element 1, element 2, element 3. We assemble those in that sort of stair-step fashion because it's linear. Pretty simple, pretty straightforward, nothing complicated there. We can reduce this problem pretty heavily because every joint is fixed against translation. Only joint 2 and joint 3 are free to rotate. So our resulting displacements will be very small. Okay? And another point we made last time is because for elements like a beam, where all we care about is vertical translation and rotation, we really don't care about the difference between a roller and a hinge if we're talking about beam analysis, because all we care about is whether or not the joint can translate vertically and whether or not it can rotate. That's the same behavior if we're talking about a roller or a pin in this regard. That only starts to matter when we look at frame analysis. Apply our boundary conditions and we get a stiffness matrix. These values are pretty large because they're associated with rotations, which tend to come out pretty small. We have a joint load vector, and then we have a force effect vector for each member. Now the joint load vector, we can write one for each member and then assemble it, but it's pretty easy to just look at the structure and write it, just like it is for trusses and bar elements and what have you. But there are no loads applied directly to the joint for this problem. So our joint load vector is 0. For each member, we refer to those fixed-in moment tables that you all have, calculate our values using consistent units, and then just using our adopted sign convention to express those values in a fixed in-force vector for each element. Make sense? We have a fixed in-force vector for element 1. Element 2 doesn't have anything because there's no intermediate loads. Element 3, we have a point load. Same story. Okay? Assemble it to get a fixed in-force vector for the whole thing. Here's where we say we've got a joint load vector. We have a fixed in-force vector. Right now we're going to subtract it. Later on we'll add it back. So we subtract it to get a fixed in-force vector for the whole thing. Apply our boundary conditions. Now we have a fixed in-force, or a force vector that we can use for solution. Force vector, stiffness matrix, inverse of K times F will give us the displacements. Same story. Take those displacements, split them up to where we have a displacement vector for each element. Take that displacement vector, multiply it times the stiffness matrix to get the force vector, but then we got to add back that fixed in force effect. Add it back, and now we get a final solution vector for the whole thing. And we took these final solution vectors, and we took each one of them and said, you can look at each one of these members and see that those forces achieve equilibrium for each one of these members. Just take any one of them, you know, some moments, let's say I know some moments here, and you will find that the sum of moments spinning in that direction equal the sum of moments spinning in that direction. So sum of moments equals 0. Excuse me. Same thing for this one, same thing for that one. Superimpose those results, and you can get your finalized support reactions for the whole structure. And it's funny how you use those to generate shear diagrams and generate moment diagrams. And then you can also take the whole stiffness matrix for the whole thing, the displacement vector for the whole thing, multiply these two. Don't forget to add back that fixed in force effect. And it's funny how that'll give you the support reactions as well. Pretty straightforward, right? Everybody good? Okay, now, what I want to do is, before we talk about frames, I want to give you this, because this has sort of been kind of a pattern of discussion for us as we, you know, have a little procedure sheet that we can go through. And I'm going to discuss this, I think, at a little bit more of a higher level than I have discussed other things, because, again, after a while, you kind of, the process is the process, and it becomes old hat. If I'm boring you with describing this process, I put 2 there, then I think I'm doing my job, because the concept of matrix analysis, you know, writing a stiffness matrix for each member, assembling it, you know, applying boundary conditions, solving for displacements, and then backing out, if that is becoming old hat, then I'm doing well. Did I get an next one? Wait. Leave him hanging, man. I'm just saying. All right, so really what we see here in this beam analysis procedure sheet is the same thing that we've been looking at. The big point I want to make, though, is we started off with this really, really basic procedure for bar elements. And then we said, well, what makes trusses complicated? Well, we got to rotate them. What makes beams complicated? This part right here, the fact that we have to subtract out that fixed in force vector and then add it back later. If you understand that, then you're good. Okay? Anybody have any questions? Okay. Now I'm going to go through this fairly quickly since you all have this. I emailed this spreadsheet to you earlier today. Did you all get this? I emailed this to your Marshall accounts. This is my Excel sheet for the example that we just went through, just to give you kind of an idea. And I think you all should be fairly versed at this point on how you would develop these things. So the way I produce these is it kind of just starts here and goes down. So these are the element stiffness matrices for each one. This is putting them where their respective locations go in the grand stiffness matrix. Here's reducing it according to boundary conditions. Excuse me. So here's the fixed in force vector for the whole thing. Here's the joint load vector for the whole thing. Subtract that out to get the fixed in force vector for the whole system. solve our system to obtain the displacements at the end, break them apart into displacement solution for element number 1 and a solution for element number 2. And same thing for element number 3. Sorry about that. And if we want, we can just do K times U, adding back that fixed end force vector to obtain the reactions for the whole thing. Everybody okay with that? I just wanted you to have that data with you. I really don't see the value in doing this again. At this point, you should be able to do it. Yeah, is the stiffness matrix a little more complicated? Yeah, the stiffness matrix is a little more complicated, but it's still plug and chug. Okay. Anybody have any questions? All right. Now, before I talk about frames, let me say this about frames. I don't expect you all to do any rigorous frame analysis at all, okay? And here's why, okay? I'm more concerned with your understanding of the conceptual issues, and specifically the conceptually tricky issues. If you can do a truss analysis, that means that you can handle members oriented at different directions. If you can do a beam analysis, that means that you can handle structures that are subjected to non-nodal forces. If you can do each of those problems, then I'm convinced you can handle those types of scenarios. What makes a frame complicated? A frame problem has both of those issues. It has members oriented in different directions, and it has loads that are applied to the members. I'm concerned that you can handle each of those problems. I'm not terribly concerned that you can handle them both at the same time. I would probably be a little more concerned with that if this was strictly a civil engineering class, but at this point, I think I'm more concerned that you understand the applications. Because the be-all, end-all for this class, the end goal is that you can open up a program and run it, which we will do near the end. So I'm just going to discuss frames and discuss the stiffness matrix just so you kind of get the idea behind what's going on, and then move on from there. Everybody good? Okay. So let me sort of get my handouts and whatnot organized. Okay, so let's talk a little bit about frames. Let me pass this out. You'll notice that my handout for frames is actually pretty light because we've actually, in all honesty, we've actually already derived everything we need for frame elements. So there's not much really to say. Do the problems get bigger? Yeah, the problems get bigger. Do they get more complicated? No, not really. They don't. So what's the deal with a frame element? If you take a truss element, what makes truss elements complicated? The fact that they can be oriented in any direction, and from a mechanics perspective, that they can be subjected to axial deformation. And then you say, all right, let's take that and then let's add to it the issues associated with beam elements, the fact that beams can bend and that they are subjected to flexural deformations. You put them together, you have a frame element. So with a frame element, we're considering everything. We're considering horizontal translation, vertical translation, and rotation at each joint. So I think some of you have probably been kind of wondering when we're going to get to this point, when we're going to get here, you know, where we can fully define what's going on with the 2D element. And the answer is right now. I guess the sad part is the actual discussion is kind of boring because everything we discussed beforehand, we actually kind of already solved the problem. Let me ask you this. How big is this stiffness matrix going to be for this member? 6 by 6, right? Because there are 6 degrees of freedom associated with this. Where do you get these terms? You just locate the appropriate stiffness terms associated with each of those mechanical relationships and plug them in. So if you look here, the ones associated with 1 and 4, does everybody see that? Okay, what is 1 and 4? 1 and 4 are the axial displacement, axial stiffness relationships. And it's funny how they're just AE over L. Everything else, look at these terms. Where do you get these? They come from the beam elements, right? That's it. there's your stiffness matrix. There's really nothing else to say. We just take all of the information we needed from the truss elements, take all the information we needed from the beam elements, and there you go. That's it. Now, I'll say this. This discussion of, and some of you might ask, well, what about all the terms that are zeros? This is what I'll say on the topic. This derivation, if you will, of this stiffness matrix assumed that the beams deform in a somewhat slender fashion. Now, the reason why that's important is because what we're neglecting is the effects of shear deformations. I'll say this about shear deformations. Shear deformations become a more critical phenomenon when you have a beam that is really, really deep. Okay? If you have a really, really deep beam, then you need to consider shear deformations. And in those scenarios, you might populate some of these terms with zeros and what have you. At the very least, some of these flexural terms will have shear deformation added to them. Okay? I'll say this. Let me say this. That concept is really more of a mechanics-based problem. You want to learn more about it? Next spring, I'm teaching Engineering 670. Take that. We'll talk all about it. All right? Everybody good? Now, what about the rotation matrix? Now this one's a little interesting. Okay? My rotation matrix has sines and cosines in it, just like last time, but I've got this 1 here. Now, what that means is that, let's think about what that means. That means that my angle of rotation stays the same regardless of the coordinate system. And that makes sense if you think about it, because, let me see if I can draw here on the screen. Before, what we were trying to do was understand how one coordinate system rotates into another, right? But this 1 here and this 1 here are associated with rotations, right? We're associated with, ooh, I can do better than that. We're associated with changes in angles, right? And if I take that, that angle change and make it 10 degrees, it's 10 degrees regardless if my coordinate system's oriented like this or oriented like that. It doesn't matter. You see what I mean? So because of that, you don't need to make it, like if you have a change in angle, you don't need to convert that from one coordinate system to another. Regardless of how the coordinate system's oriented, 10 degrees is 10 degrees. What needs to be rotated is whether or not our displacements are acting this way or acting this way, because we're talking about a translated distance from one point to another. That matters if we're talking about coordinate rotation or coordinate translation. Rotations, it just doesn't matter. Does that make sense? An angle change is an angle change. Everybody good? All right. Okay, now I have this problem here. This is a frame analysis example. Excuse me. Let me say this about this frame analysis example. We're going to go through this problem really quickly. Okay, you all have the Excel sheet with you. I don't have any slides prepared for it because I'm really more interested in us just going through the analysis procedure. There's a couple things I want to mention though. Okay, here's our, well, first off, so here's our frame and here's the analysis model. Should be fairly straightforward, right? So the system level stiffness matrix is going to be 9 by 9. Everybody okay with that? Okay. Now, does this frame have loads that are non-nodal in nature? In other words, does it have loads that are applied on the member? Yeah, we got this 40 kips, and we got that. do we have loads applied directly on the joints for this problem? Yeah, yes we do. This one right here, that is a joint load. It might be a moment, but it is a load applied directly to that joint. It is associated with degree of freedom 6 for the whole system. Would it be a positive load or a negative load? There we go. See where we're getting this? I wanted you to recognize that that is a joint load. Everybody okay with that? Okay. That's one thing I want you to recognize. That's a really obvious point. There's also one that's really subtle, and it is associated with this member. We are going to have to perform rotation for this problem because this member is oriented, horizontally, but this one isn't. This is a vertical member. So now not all of the members are oriented in the same direction. Make sense? Okay. Because of that, we have to perform rotation for this. Now that's an easy thing to understand. What isn't so easy is when we start dealing with the fixed end forces associated with this member. And again, I just want to make sure that you understand the general concepts. Everybody good? Okay. So let me walk through this frame analysis example very, very briefly, okay? But I'll spend time on the things that I think are important. So remember, let me zoom out a little bit so we can kind of see what's going on. You all have this in front of your screen so you can follow along with me. Here's my frame and here's my analysis model. So I can write coordinate information here. Bless you. Based on that coordinate information, I can determine all of my member properties. The big one being, remember delta x's and delta y's. We always take the higher value or higher nodal x value or y value minus the lower number. So if we're looking at member number 1, we would take x2 minus x1, y2 minus y1, right? Make sense? Okay. Let's also talk about member coding. So its first element associated with 1, 2, 3, 4, 5, 6. Second one, 4, 5, 6, 7, 8, 9. Everybody see that? So the assembly will be pretty simple, okay? Let's walk through that. Okay. Starting off with element number 1, remember, local stiffness matrix, rotate it into a global stiffness matrix, and then those terms go right here, right? Right there, 1, 2, 3, 4, 5, 6. Second element, local stiffness matrix, rotate it into a global stiffness matrix. Those terms go here, okay? Assemble them. Assemble them into a global stiffness matrix for the whole thing. Everybody good? Reduce it and see what we're eliminating. 1, 2, 3, 7, 8, 9. 1, 2, 3, 7, 8, 9. Why are we eliminating those? It's a fixed support. Fixed supports resist translation in both directions as well as moments. So this will be a 3x3 system when it's all said and done. Now watch this. My joint load vector, it's not full of zeros, is it? How did I get that? What is that negative 900? It's the moment, right? There you go, exactly. It's a 75-foot kip moment, but that's feet kip. Feet, consistent units. So 75 times 12 is 900. That's where the value is coming from. It's negative because it's applied in the opposite direction. Make sense? Okay. Now, this is a little more of a subtle point, so I'll take my time with this one, and it's subtle, but I'll just kind of explain what's going on. Let's talk about the local fixed-end force vectors, right? So how do the local fixed-end force vectors work? This first one, It's a beam with a point load at center, right? Beam with a point load at center. Based on that, I can determine my reactions and end moments from my fixed end force tables that you all have handed out to you, right? Okay. Now, I rotate that, however, to get global fixed end forces. Now, what's interesting is look what happened. Look what happened from here to here, okay? Did the moments change? Now, remember, we have horizontal, vertical rotation, horizontal, vertical rotation. So 1,200 and minus 1,200. Over here, 1,200 and minus 1,200. Did they change? No, because the moment reactions are the moment reactions. But one thing that is kind of interesting is look at this. These switched and they changed sign. Does everybody see that? They switched and they changed sign. Here's why. We're talking about the rotation. Oh, it's easier to just kind of draw it out. We're talking about the rotation between a global coordinate system and a local coordinate system. So this might be my element, right? Now let's go back to what we said before. These are local displacements, right? Okay? And then we have those right there, right? Watch this, okay? I want to take a moment. I want to look at this picture, okay? Now let's say my angle of orientation is, I'll make up a number, 0 degrees. Would you agree that that element would look like this? And these would be the local degrees of freedom. Would you agree with that? All right, let's make up another one. Let's say theta is 45 degrees. Would you agree we're going to have an element something about like that? And its local degrees of freedom, what are they going to be? Something about like that, like that, like that, like that. Everybody see that? So let's look at what 90 degrees would look like. So 90 degrees, we'd have an element that looks like this, right? Getting a little bit of lag on my screen here. All right. So what do we have? We have up, up, but then this is going to the left, right? Left. And then, right? That's a little weird, isn't it? Because I thought right was positive. But here we've got left being positive. Do you see that? What happened between the translation of local to global coordinates right here? These switched and they became negative. Why did that matter? Well, they switched because we went from looking at a local set of coordinates, which is what you see right here, to a global set of coordinates. And if you look at the difference between local and global, these terms are switched, and it's funny how that one's going in the opposite direction. Look what happened. Terms switched, and the signs changed. How funny how that works, isn't it? Make sense? Now, there's no difference between the local and global on element 2, but that's because look at the beta matrix. It's just the identity matrix, and the member's flat, so there really is no difference. Does that make sense? All right. Any questions? All right. So that's a subtle point, but I think it's worth making. We assemble those fixed end force vectors to obtain a fixed force vector for the whole system. So here's my joint load vector for the whole system. Here's my fixed end force vector for the whole system. I got to subtract it now to get an answer, add it back later. So reduced forces, reduced stiffness gives me reduced displacements. I can calculate the response for each member accordingly, add back that final answer, and then compute reactions, and you all have this in front of you. Now, what you're seeing here, these images here, are captures from a structural analysis program called RESA. RESA utilizes matrix analysis procedures to do all of its math. If you take me for undergraduate structural analysis, that's what we use in that class. And these are the answers that you get from RESA. Basically, the way, like if you take me for an undergraduate structural analysis class, what happens is I kind of just show you, here's this software, you draw some lines, put some triangles and circles for rollers, put some loads on there, and it just spits you out an answer. This is how it does it, okay? Here's the reactions, and then from these reactions, as well as the free body diagrams and the solution vectors for each individual member, we can draw a shear diagram and a moment diagram for the whole system. I don't expect you all to get into that much detail because you all have undergraduate degrees in engineering. I promise you, I know you've drawn a shear and moment diagram before. It might have been a while, but I know you've done it. So you don't need to prove it to me again. But I do want you to understand the matrix analysis procedures. All right. Is everybody good? Does anybody have any questions? Okay. All right. Just for your own edification, I prepared a matrix analysis procedure sheet for frames, and I don't expect you all to use it in any great detail. It's more so that you all just understand the difference between what it is we've been discussing. Okay. All right, everybody good? Now, what's funny is, you're going to laugh. So we've been talking about this stuff now for what? Like 3 weeks, 4 weeks? I think now maybe we ought to start talking about finite elements. We actually haven't talked about finite elements at all, okay? Here's the thing, okay? When we do matrix analysis, I'm going to hand you out this in a second. When we do matrix analysis, would you agree this is really what we're after? This is the whole problem, right? That the force equals stiffness times displacement. And what we're after is defining these matrices, the force vector and the stiffness matrix. Once we have that, it's just matrix math to get the displacements. Now, up until now, we have been using what's called a direct stiffness approach. The direct stiffness approach being, here is a bar. Take that bar, yank on it. What is its response? That is a direct approach. Actually physically loading the bar and monitoring its response. That's fine if you're dealing with members that are simple. Bars, beams, trusses, things like that. It's easy. That's simple. When you're dealing with a 3D model of a V8 engine and you're doing thermal and mechanical stress analysis in the nonlinear range and you're using tetrahedral elements and brick elements, direct stiffness doesn't work, okay? Are you using the same general procedure? Write a K matrix for each member, assemble it, apply boundary conditions, solve for displacements, yada, yada. Yeah, it's the same procedure. The problem is, how do you get K? How do you get F? How do you take a brick element and take that one node and move it this way and record its force? That's tough, okay? So I propose that we need to develop a different approach if we want to do real problems, real complex two-dimensional and three-dimensional problems. We need to do something differently. So I propose to you that there is another way that we can develop those stiffness matrices. And that procedure is to use something called the finite element approach, okay? Now, it's going to take us a while to explain that. We are not just going to dive into it, okay? I will give you the 30-second version right now, and then we'll take the next couple days explaining it. It might feel like movie time for the next couple lectures, but I want to take my time and explain this. But basically, what the finite element method states is we do two things. One, we make a guess based on a given element. We make a guess on what that displaced shape of that element looks like. I mean, before we were talking about degrees of freedom, and we said how many degrees of freedom defines what the displaced shape looks like. We're going to make a guess for a given element. Then, based on that guess, what we're going to do is compute energies. Okay? You all taken physics. You remember that fundamental energy balance problem. I got a tall building, and I got a ball on top of the building. I kick the ball. What happens? On top of the building, that ball has a stored potential energy of the mass times the gravity times the height of that building. And when I kick the ball, that energy gets converted into kinetic energy at the bottom, 1/2 mv squared. And then using that energy balance, I can determine what's the velocity at a given point, et cetera, et cetera. You've done problems like this before. We're going to do the same thing, okay? But making that assumption about what the displaced shape looks like, and then using that assumption to compute energy balances, that's finite elements. That's what it is, okay? So we're going to take a little bit of time and talk about that. It's going to take a while, but I want to sort of take my time with it and make sure that we're good, all right? So I'm giving you all sorts of stuff today. Now, I'm not going to lie, some of these notes I sort of pull from my undergraduate structural analysis class, but a lot of this stuff is the same, so it's fairly straightforward. But we're going to take our time one by one. So let's start off with something simple. The law of the conservation of energy. It states that in a system, energy can take all different types and forms and what have you. We can have gravitational energy, potential energy, kinetic energy. We can have thermal energy, mechanical energy. We can even get electrical and magnetic, what have you. But the fundamental principle is that energy cannot be created or destroyed. It can only be converted from one form or another. That's one of the reasons why finite element analysis works for problems beyond solid mechanics. This procedure, this type of analysis, was originally developed for solid mechanics problems, things like fundamental structural analysis. But when you use an energy conservation approach, you can use finite element analysis for heat transfer and fluid mechanics and all of that stuff, because it's all based off the same principle. The law of conservation of energy. Energy cannot be created or destroyed. Make sense? Okay, so to keep this basic and not, write expressions on, 80 different types of energies in a system, we're going to keep it simple, okay? I propose that when we're looking at systems from a solid mechanics standpoint, a structural analysis standpoint, we really only need to consider two energies. The work done on the outside and the energy stored on the inside. Let me give you kind of an idea. So I'm sitting here at this lectern, and I've got this sort of extended table, platform out here. Let's sort of imagine that this is a cantilevered beam, okay? Now, I've got this weight in my hand. I usually, like, if there's a table in front of me, I usually sit on the table, but I'm not sitting on this thing. That would be bad. I feel like it does not have a large enough K matrix to support me. I got jokes, but but to give you, just for the sake of discussion, so this beam has an associated stiffness with it. Now, if I take a load and I place it on this beam, what does this beam do in response? It deflects, right? So let's think about this from an energy perspective. How do we define work? It is force going through a certain distance, right? So this has done work to the table, or to the beam, right? It has done some work. The beam responded by deforming. By deforming, it has stored energy inside. We call that stored strain energy, all right? If we can equate those two energies, we can determine, well, how far did this thing deflect? That's the whole point, okay? So I want to look at this from an energy perspective. Okay? So we'll go back to basics. If I have some linear elastic medium, I apply a load, I say force equals stiffness times displacement. Now, if we're talking about this from a linear perspective, and I apologize for breaking this out a little bit. You are going to see a little bit of this. You all knew this well going into this, but I have sort of a funny statement that I make about college curriculums. Like if you ever go to like a Thai food place or a Mexican restaurant, and you notice, you look at the menu, and you know how some items on the menu have like a chili symbol next to it? What does that mean when you order the item with the chili symbol next to it? That's a spicy, so watch out, right? I think that when it comes to a college curriculum, that some of the classes should have like a chili symbol next to it, because that chili symbol indicates which classes have calculus in it. This class has a chili symbol associated with it, but really only for discussion purposes. We really don't get too much, into this. Okay, I use it solely to kind of express what it is we're talking about from a conceptual standpoint. We might do a little bit of calculus when we actually derive elements, but I promise you that the calculus that we do employ in here is very simple. What's the derivative of 2x? 2. You're good. You're good. Really, that's about what we see in here. Derivatives and integrals of polynomials, like the derivative of x squared or x cubed. If you can do that stuff, you're good. All right. So, excuse me. So, going back to this problem, we recognize that there is a relationship between force and displacement, and that relationship is stiffness. I want to look at this from an energy perspective. So if I plot the relationship of force and displacement, up until now we're assuming that's a linear trend, right? We apply more load, we get more displacement. More load, more displacement. More load, more displacement. There is a slope, if you will, a relationship between force and displacement, and we call that stiffness, right? Okay? Well, if I want to determine the work done to this system, or the energy that has been exerted by a given load acting on that system, I might integrate, right? Well, this is simple. This is just a triangle, right? So the work done by an external load is the force times the distance over 2. See where I'm getting at? It's just a triangle, right? We're going to use a little bit of a creative technique later to get rid of that triangle, but again, this is solely for discussion purposes. And also, I guess I should mention that we can do this for force and displacement just like we can do this for moment and rotation. Okay? Everybody good? Now that's external work, and there's not a whole lot more really to say about external work. Okay? Now, what about stored strain energy? Stored strain energy is how a member responds to a given load, how it deforms to maintain equilibrium, okay? Because things deform, okay? That's what we learn after we take statics. When we take statics, we assume everything's rigid. Then we take the next class and we find out that was all hocus pocus, that really things deform, okay? Now, things deform in all sorts of ways, and for each level of each type of deformation, we have a different set of mechanics associated with it. Let's take an axial force element. If I take a member and yank on it, it responds with some deflection delta. If we're looking at a little increment, we might say a little d delta. And we say, well, the internal energy, based off what we were talking about earlier, is the force times the displacement over 2, right? But now we need to start getting into the mechanics a little bit. What is this relationship? Let's think about this logically. What's the relationship of this to this? Isn't that, what is it, the change in length? And this dx, that's the original length. What's another word for the change in length divided by the original length? That's the strain, exactly. So this d delta over dx, that's the strain, right? And now we're talking about axial force. So the strain is defined as the stress over Young's modulus, which is defined, what's stress? It's P over A, or F over A in this case, right? So I can do a little bit of substitution, go back to my integral, plug and chug, and now I have an expression for the stored energy inside a bar, right? So you think about it, if I have the stored energy inside a bar, which is the force inside that bar squared times L over 2AE, and I know the force that caused that stored energy, it's funny how I can set those two energies equal to one another and solve for the displacements, right? Pretty straightforward. Now, does that compare with what we did before? This is a pretty simple approach, so let's think about this. You agree with this relationship, that the idea that, you know, force and displacement are linearly proportional to one another, right? Well, if I apply some force to a bar, it deflects PL over AE, or FL over AE, right? So what's the area of this triangle? 1/2 of that times that, right? Plug and chug and we get the same answer we just looked at. Make sense? Everybody good? Okay. Now that's force, okay? Let's talk a little bit about moment, just to sort of expand the discussion and make sure we're all seeing where this stuff's coming from. Same concept. It applies to moments and rotations as well. If I take a beam or a beam element and apply a bending moment, it's going to respond by changing some angle, force times displacement over 2, or in this case, moment times rotation over 2. That's going to be the stored strain energy inside that element. If I integrate that over the beam, I get the total energy inside that beam. Now let's bring it back. Remember this? I know you've seen that before. I know you've seen it before. That is the Euler-Bernoulli beam bending expression. That's the diffie-q that defines beam bending in general. That the second derivative of deflection is m over EI. Everybody's seen that in this room. I know it might have been a while, but I know you have. So I can redefine my, I can redefine my rotation as a function of the associated mechanics, integrate over the length, and get the same type of idea. So I'm dealing with these similar terms, you know, the force effects and the stiffnesses associated with the given mechanics. Everybody good? Now, here's the problem. That all sounds nice and neat. What the heck are we talking about all this stuff for? Well, first off, I want to give you a little bit of the understanding behind the energy principles associated with how we derive finite elements. So you might say, well, that's good, right? We don't need to talk about it anymore. You've hammered it into the ground, right? No, we've got another issue, okay? The problem with the discussion that we've had just now is this. Let's go back to my little beam that doesn't have a large enough K matrix for me to sit on, okay? Here's my beam. I take a load, I apply it right here. And I'm applying it right at the tip of the beam, right at the very edge, okay? So far, everything that I just discussed just now only works for calculating the displacement right here, where the load is being applied. I take a load, I apply it right here, I can only get the displacement right here. What if I don't care about the displacement right here? What if I want the displacement right there? Then it becomes a problem. Because this concept of energies equaling one another, the math I just wrote only corresponds to the point of application. Okay? So that works if I only care about determining deflections where the loads are applied. But that's not always the case. I mean, I can think of any number of scenarios where you have a load applied, but you care about the response somewhere else. That happens all the time. So maybe we need another approach. And that's where virtual work comes into play. Up until now, we've been talking about real work, real loads, and then the real response. What about virtual work? Virtual work is a trick that we pull. What we do with virtual work, and it's a little strange, but the long and short of it is it makes sense when you think about it. For virtual work, what we do is we say this. Anytime we write an energy principle, it only works for where we apply the load. So we say, all right, is that how it's going to be? Then we'll just apply another load. we'll apply a load where we want to determine deflections. Now, if you took an undergraduate course in structural analysis, you might remember the unit load method, where you take a structure, you analyze it, but then you take like a 1 kip force or a 1 kilonewton force and then apply that and do the analysis again. That's what this is, if you remember that. But we'll walk through this step by step and kind of explain what's going on. Now, so to formalize our discussion, I got a cantilever beam here. It's being subjected to some load Q, and I want to, right now, everything I've done says I can get you the deflection at C, no problem. That's simple. Right now, I'm asking, what if I want the deflection here? Energy principles say I can only determine that deflection if I put a load right there. Well, fine, I'll put a load right there. Okay? So I'm going to preload the structure, if you will. I'm going to put a load P on that structure. The magnitude's actually not going to matter, and as we're going to see in a little bit, if you wanted to do this analysis by hand, you'd make the value 1, because anything times 1 is itself. So I'm going to preload the structure with P, and then I'm going to put Q on it. Now, you're going to see here when we start equating the energies that ultimately that effect will get canceled out, and you'll see how this works. But the idea is this. P's not really there, but we're going to use this fictitious load to simplify our energy calculations and allow us to compute deflections anywhere. Okay? So you all are okay with this, right? Y'all are okay with that, right? So what I want to do is look at this curve again and ask ourselves, what would the curve look like if we went with this preload? Okay? So the first thing I'm going to do is I'm going to load it with P, and then I'm going to, which is a made-up load. I made it up. Dr. Michelson just said, let's just put something on there. And then we're going to put the real load on there. Everybody good? So here's the load deformation curve. So that's the preload. So I put some load P on there. It responds with some deflection, delta sub P. Then I put the real load on there. Okay? So the real load, so think about my curve. Think about this as if it was a graph. I put a little bit of load, then I put my real load. So when it's all said and done, the final load on this curve is P plus Q, right? The final deflection is due to P plus Q. Make sense? What I care about, though, is this. I care about this dimension. Make sense? That's what I'm after, the deflection due to those real loads. Everybody good? Okay. So you're going to see something kind of interesting. What we're doing now is we're doing the same thing that we did before. We're computing the work inside these elements, right? It's funny how we're not dividing by 2, right? Remember how we did force times displacement over 2? There's no 2 there, right? Because we're not looking at a triangle, we're looking at a rectangle. That actually makes our lives a whole lot easier down the road. It's a subtle point, but it'll make things nice way down the line. Everybody good? Okay. All right. So I want to summarize what's going on here. So here I've got this structure. This is, when it's all said and done, this is its preload and this is its final load, right? Now, I propose to you that we now have 2 expressions for the work done to this system. The real work, load times displacement over 2, but we now have this virtual work. Now, one thing to notice, the 2's gone, right? Everybody see how the 2's gone? That makes sense, right? Because we're integrating the rectangle. That's number 1. But number 2, I want you to look at the terms. This one is a function of delta C, where the load's being applied. This one, a function of delta B, where the load's being applied. This one's going to be more valuable to us because that's what I asked you in the beginning. I said, what's this deflection? I don't care about the deflection here. I want that one. Make sense? I know it's a lot of theory. I know. It'll be all right. We'll get through it. I promise. We got to take our time with this, because if I just say, oh, by the way, here's B transpose CB, you go, whoa, you know. All right. Okay. Everybody good? All right. So this concept of that 2 going away kind of applies across the board. It's not just the external work done, it's the stored strain energy. So if I was looking at stored energy inside the element, it would be md theta over 2, but for virtual strain energy, it would just be md theta. And I use like capital M versus little m to sort of differentiate between real moments and virtual moments. Everybody okay with that notation? I mean, this is just for discussion purposes. Right. Excuse me. So the nice thing about, you know, what's going on later is again, and this is probably just hammering in that point that we were mentioning later, but that 2 going away will actually make our lives a little easier way down the line. But my point is that we can use these virtual moments just like we use, or virtual energies just like we used the real energies before, and carry out that same process. Integrate across the section and calculate the total energy inside the whole thing. The nice thing about this approach is we can calculate those resulting rotations or deflections anywhere. Okay? Everybody good? All right. So I want to take a little bit of time and digest what's going on this slide. So first off, the top line, U equals W, the fact that the stored energy inside this system must equal the external work done. That's just law of conservation of energy. I don't care what's going on. Everything going in has to equal everything going out, otherwise the beam's running away from you. See, think about it like this. All right, we tend to say U is stored energy and W is external work done. There's also, later on, we might look at T, which is what we define as kinetic energy. That becomes important when we do like vibration problems. Now, to give you kind of a descriptive understanding, U would not equal W if I really did sit on this beam. Because if I did, what would happen? The beam would probably fail, and then I would not be very happy because I fall and hit the floor. So there's a kinetic energy associated with it. But for it to remain static and stable, the internal energy stored has to equal the external work done. Everybody good? Now, the whole point of this discussion is that we've been able to split these up into 2 components. The work done as a function of the real load and the work done as a function of the fictitious fake load. Now, the nice part is that our formulation down here, look at this. We've got differences between real load, virtual load, virtual load, but they're all functions of the real displacement. See that? Real load times real displacement. Virtual load times real displacement. Real displacement, real displacement. That's the nice part. Now, what I'm going to do is I'm going to pull, this is where it gets nice. I'm just going to cancel those terms right there. How can I do that? Law of conservation of energy. Real work on the outside has to equal real work on the inside. I can cancel those. And it's funny how all those terms associated with that 1/2 go away. Why do they go away? Because now I'm only considering that rectangular portion of the curve. Everybody good? It's a subtle point to make, but later on down the line, when I just get rid of a 1/2 and I show you these equations, all the 1/2 doesn't matter. How did you just cancel the 1/2? This is how. Make sense? Okay. So using this virtual work approach, we can compute deflections anywhere in a structure. Okay? We end up letting our unit load, or our load equal 1 for simplicity. And I'll also add to this, when you take an undergraduate course in structural analysis, or you might even do this in strength and materials, you might do virtual work stuff for beam deflections and what have you, you use this I guess what I'll say from a very strictly defined, approach. You take simply supported static, or, you take statically determinate beams, maybe they're simply supported, maybe they're cantilevers, what have you. Very simple loading scenarios. And based on those conditions, you can do this by hand. What I want to do is use this more from a conceptual standpoint. I want you to understand this idea, because it's these ideas that we're going to use to develop larger analysis issues and larger analysis strategies for more complex problems. What are the takeaways that I want you, the big takeaways I want you to get from this lecture? Number one, instead of using a direct approach, we can use an approximate energy-based approach to derive elements. Okay, that's number one. Number two, we do that by saying the energy inside equals the energy outside. Point three, we eliminate this 1/2 term by employing a principle of virtual work as opposed to a principle of real work. By doing that, not only do we eliminate this 1/2, but it allows us to not compute the deflections just where the loads are applied, but we can get the deflections anywhere. Everybody okay with that? Okay. That is one very restricted piece of information that we really need to understand before what comes next, which is the second part of finite elements. I guess the second part of our basis, if you will. If you remember how I described the finite element approach earlier, I said, yeah, we use energy approaches, but how do we use those approaches? We use them by assuming what the displaced shape looked like. We guess, okay? That to make that guess and to understand what that guess means, we need to talk about these, shape functions. We'll talk about that next time, okay? But I really want to let this info sink in, okay? Now, real quick, in terms, before you leave, we've got a few minutes, and I want to talk and make sure you all understand what's coming next, okay? So here's what's coming next. You all have a homework assignment due on Thursday. On Thursday, I'm going to give you another assignment. It's going to be a beam problem, okay? It's going to be a shorter assignment because by its very nature, beams, I think, are simpler problems from an Excel standpoint. There's less matrix multiplication. The problems are a little more contained. So I'm going to give you a week on that. So it's going to be due next Thursday. That's going to put us into week 5, okay? What I want to do for this class is this. I don't want to load too much material on an exam. So this is what I think I'm going to do. After you turn in the next assignment, I'm giving you your exam. Take home, okay? I am not going to give you 6 trusses and say analyze the whole thing. It's not going to be like that, okay? It's going to be a series of conceptual questions, and then I'll give you some problems, ask you a few pieces of information. I did this last semester, and the take-home exam was pretty quick. It wasn't anything that took hours upon hours, okay? But you all are grad students. You all can do it at home. A couple points. There's only 2 exams in this class. This is what I think I'm going to do for this class. Exam 1 we're going to do next week. So it'll be like right at the end of week 5. Exam 2 is going to be right at the end of week 10. We're not going to have a final exam. We're just going to have our project at the end. That's how we're going to end the class. So no be-all, end-all final project or final exam. It's just going to be a project. Sorry about that. So does that sound fair? I think that works for this class because the way this class is, we'll spend the next 5 weeks discussing finite element theory and applications, and then we say, shut all this off and let's start opening the software. So we really switch gears literally right around week 10 or so. So I don't really see the point in, trying to lump in this theoretical discussion, for a final exam when you have a project going on anyways. I'd like to spend more time on the project anyways and give you all time to define something a little more rigorously, especially for you grad student mechanical folks because you've got projects, real projects coming up. What was I going to say? Do you all have any questions on stuff? Okay. All right. So that's all I've got for now. Your homework's due on Thursday. Just email it to me like you have been. And that's it. That's all I got. All right. I'll see you all next time.